We'll invite him back again when he has the whole record, back to 14,000 years. And when you get to, 4.6 million or something, we'll have you come back again. That's a long-ass core. Moving right along. Next, there's a little change on your agenda. Camera Naficy was not able to be with us today, but one of his co-authors is going to deliver that talk. It's Meg Krawchuck. She's an associate professor here at Oregon State University in the School of Forestry. She's going to be talking about fire refugia, old forests, and northern spotted owls, a synthesis of clear concepts, trends, and tool sets for local to regional conservation planning. So tell us how to make it work. Ready?
Yeah.
Okay.
Off we go.
Help me welcome Meg, everybody.
Yeah. Hi. And it's so great to see everybody here. This is really wild to see so many faces. It's a little uncomfortable, actually. We also have co-author Jeremy Rockwaite. He'll be presenting a little bit of the end bit here. So bringing together some of the work on fire refugia that we've been dabbling with for many years now, blending them with conservation interests in thinking about old forest and spotted owl conservation. This is a neat little setup here. So co-authors, I can look down here, I guess. Cameron Naficy as lead, Ray Davis, Jeremy Rockwaite, Garrett Meggs, Matt Riley, Jiquang Yang, Stacy Jury, and me putting up the tail there. All of this work moving forward. So fire refugia in the Pacific Northwest. I want to get us into some terminology to start off. Gosh, what are these things that we're talking about? They're the places that burn less frequently or less severely than the surrounding landscape. So when we've been thinking about these patterns of burn severity, I'll speak into the microphone. Speak into the microphone. There are these places that burn less frequently or less severely. I want to highlight that these places are not necessarily unburned, and in fact, low severity fire or underburning is actually critically important to maintaining some of these refugia moving forward. And so we're thinking about these as places that are refugium or a refugium from high severity fire, sort of an easier dichotomy there. Why are we thinking about these fire refugia, these concepts? Wildland fire is an important ecosystem process that supports biodiversity, but at the same time, we have increasing worry about erosion of ecosystem services due to increased severity and types of fire. So we've got some icons there on the screen. A northern spotted owl, when we're thinking about severe losses to high severity fire, increasing concern about loss of owl habitat. To fire, we look at the picture at the top right, or sorry, at the top left here, showing scorch patterns in old growth forest high up onto the bole of the tree, but maintained as fire refugia. And we heard from Andrew and a number of other folks today just thinking about this role of fire in cultivating and curating older forests through time in the region. And then that satellite photo on the far right showing the 2017 fire hotspots, the smoke in the air, sort of the beginning of our wake-up call in our wet side forest to thinking about the role of fire at a big scale. So this is a graph from Ray Davis and the Northwest Forest Plan monitoring cycle. We see fire, or we see years across the x-axis going back to 1986, and on the y-axis we've got federal lands in the region, millions of acres. And we've got a couple of different things going on in this graphic. We've got those red bars showing area burned, fire activity ticking up, 2017 and onward. We've got that old growth metric across the region in the light and the dark green, showing sort of a steady, relatively steady bar through time up until those later years where we start to see losses, as well with northern spotted owl forest or northern spotted owl habitat and this concerning drop-off as we interact with more and more fire. So how do we plan for conservation in the face of increasing fire activity? And that's where this fire refugia work and the fire refugia project has stepped in to help with our thinking about the places on the landscape that persist through high severity fire. So the goal of this project was funded by the USGS Northwest CASC back in 2017-2018 time period, was to map fire refugia in the Pacific Northwest, to model the drivers of fire refugia? Where do they hang out? Where is that hang time located in geographic space? And then to share with scientists and managers. This nice call out to Cheryl's starting bit here of communicating and working together and figuring out ways where the science we do can crosswalk into management actions. So, map on the far right shows the study region, essentially the bioregional assessment area of the Northwest Forest Plan. You see the yellow, that's a drier forest, or the yellow is a moisture forest component, and the red is a drier forest component, and we divide up the region into. And when we're thinking about these drivers, we're using our friendly neighborhood fire behavior triangle to think about fuels, topography, and weather as constituent pieces of where fire refugia occur on landscapes in contemporary fires. So today I'm going to whip us through really quickly some of the work, a brief overview of what I call the fire refugia suite of models. What are the patterns and drivers of modeled fire refugia probability? Including these ideas of blow-ups and normal fire weather and where refugia persist under those. We've seen that theme come up multiple times today of these different, really phenomenally different behaviors in blow-up versus normal conditions for fire spread. And then we have two case studies to explore fire refugia models in general. This is the touchdown piece of, gosh, how does the modeling work with conservation needs and planning, sort of testing them out to see how they work in the world of old forests and the world of spotted owls. So looking at testing against 2021 fires, as well as looking at northern spotted owl habitat and northern spotted owl demography to understand how our fire refugia models can help us understand persistence of those features on the landscape. I'll give a call out, a nice pickup from Brian's a little round tour of call outs earlier this morning. Come check out our poster if you want to find out some more details of what I'm talking about here. So, the models of fire refugia and severity. I'm focusing on fire refugia here today, but we also have fire models for intermediate severity fire and high severity fire that sort of all play together in understanding this contemporary geography of fire. The moist forest region, the dry forest region, you can see in those different colors, and two scenarios of models, fire weather and a fire weather plus fire growth, or sort of a blow-up-y term that allows us to get at some of those behaviors. These are boosted regression trees, sort of statistical models. Not going to go into a lot of detail other than to say that we have a response variable, 1, 0, are you a fire refugium or are you not, based on Landsat burn severity mapping. Using a 10% basal area mortality as our cutoff there, and a whole suite of explanatory and exploratory variables, vegetation fuels, topography, daily fire weather and climate, and this fire growth variable that I'll tell you a little bit more about. So we're using contemporary data, 2002 to 2017, and then we tested on the 2020, 2021 fires that I'll show in a bit. A bunch of fires to sample from and using a sparse sampling procedure there. Do not read this table other than to see that we use vegetation, topographic template, fire weather, and fire growth as those explanatories, and ask a bunch of things about how these different variables might contribute to explaining spatial patterning in fire refugia. These are spatial hypotheses, essentially, about how fire works in terms of fire effects. This fire growth term I want to introduce us to is essentially this extreme, or essentially allows us to understand when fire is moving more slowly versus more extremely, fast or rapid extreme fire spread events, using that MODIS hotspot methodology that we heard about from Crystal, I think it was Crystal, earlier this morning. So we're including that as a term in our statistical models. When the particular pixel burned, was it burning under conditions where the fire was moving slow or moving really fast? And what we see are really different fire effects in terms of refugial patterns under those different conditions. So I'm going to be talking about different model scenarios, the fire weather and fire growth models. And those are ones that only include fire weather terms in them, and then the model that has fire weather terms as well as fire growth. So that was a whirlwind. That's our modeling setup overview. And I want to just give us some key model outcomes here before we get into the weeds of digging into some of those case studies, which is where I think some of the really exciting and interesting pieces come to play. So I've got some panels up there on the left. They show the statistical response curves. Don't look at them. Come to the poster and see them. But they show these variable relationships that are interpretable and intuitive based on what we know from fire behavior, which is promising. What we see is that in both of those ecoregions, the moist and the dry, they have broad similarity in drivers. We've got vegetation and topographic template playing a key role as predictors. Biomass, functional traits being of key importance, topographic position being of key importance in terms of whether you maintain or are persisting as fire refugia. In particular, live tree biomass, an old growthiness characteristic or a mature and old growthiness characteristic, gets you increasingly likely to maintain or persist as fire refugia. Topographic template, low slopes, valley bottoms, and northwest aspects, again, shouldn't be a surprise. All of these pieces are kind of known from what we know of fire behavior, but here we have them pulled into a model statistically that allows us to make predictions across a geography. That's the really winning mix here. And then from those fire weather variables, we see higher temperatures and lower relative humidity, essentially vapor pressure deficit, are eroding fire refugia. And so we have these, as I mentioned before, these key model outcomes that match with what we kind of already know about how fire works, but wrapped together in this multivariable model. So what this allows us to do is develop map predictions of persistence of fire refugia across this entire region. Using the fire weather only model, we can develop these neat scenarios under low, moderate, and extreme RH min and T max because of those relationships. Similarly, with that fire growth and fire weather model, we can make predictions about what happens at 10th, 50th, and 90th percentile conditions for RH min, T max, and fire growth as well, those blow-up conditions. So blow-up fires and quote-unquote normal fires. And you can see I've got a couple of panels over there on the right. We've got this neat web tool, this EcoVis web tool that allows you to go into particular geographies and explore the spatial patterning under different scenarios, as well as a neat little gadget at the bottom that shows the variability in drivers and how they change spatially across the landscape. So, running along here, case study 1. Here we go, touching down into seeing, okay, we got these models, they seem to make sense. We've got a good groove going here. How do they play out when we tackle out of sample validation and understanding what we see across the landscape? Case study 1, exploring with the 2020-2021 fires. Here, we divided up the fires within that sample into being either quote-unquote normal fires or those that exhibited fast rates of spread. Those are blow-up fires. And here what we have on the y-axis is the mapped RDNBR, so the burn severity on that y-axis. And then we've got old growthiness on the x-axis. We've either got not old growth, that's the other, core or edge old growth. What we see in that first panel with the normal fires is that burn severity tended to be lower in old growth, either core or edge. When we go into the blow-up fires, everything burned hot and high. So you're losing most refugial qualities. So that just gives us thinking about crosswalking to old growth. Here's the crosswalk that actually goes to our fire refugia models. So we've got these models that we built from 2002 to 2017. Can they provide some useful prediction about what we saw in 2020 and 2021 under normal fire conditions and extreme or blow-up conditions? What we'd expect to see, and I've got the mean RDNBR on that y-axis, and then we've got our predicted refugia probability on the x-axis. If these models are doing relatively well, we expect to see that negative relationship. I won't go through much of the detail here, but we do see overall a negative relationship showing that our models are able to predict future outside of the building conditions, do a reasonably good job in most cases about thinking about where across the landscape we have fire refugia. Under both normal fires and relatively well with blow-up fires, there's a little bit more trickiness that goes on in there. But I think it's particularly exciting to see that we do have that relationship that we would expect to see under those blow-up conditions. That means we've got something durable here, even under those most extreme events. Case study 2 is thinking about northern spotted owl and fire refugia. So I want to think about northern spotted owl habitat in relation to fire refugia. How are those co-playing on landscapes? And then demographics, and that's where I'll hand things over to Jeremy. So this first one, it's a tale of two wildfires looking at northern spotted owl habitat. We've got a geography here for reference, the study region, and you can see we're looking at the Slater fire. Both of these are 2020 fires, and the red salmon fire in the Trinity Alps wilderness. We'll get off free by saying this is in Oregon because the Slater fire has a little nibble that goes into Oregon. So these are different kinds of fires. One would be considered a blow-up fire, and one, quote-unquote, a normal fire. And so that patchwork that we see is the burn severity across those landscapes. So the red salmon fire just sort of crept its way around, moving across that landscape for about a month, resulting in this fire effects pattern, with red areas indicating high basal area mortality, and the bluer areas are fire refugia. Here's northern spotted owl habitat. Back to 1993, mapped using the Glenn et al. Method for mapping northern spotted owl habitat. You can see suitable in green, and in beige we've got not suitable across that Trinity Alps landscape. Here we have a wildfire in the 2000s overlaying on that patchwork. By 2017 we see this nibble back. I'll just sort of compare those two, back and forth, nibbling back. Then we have the 2020 fire across that landscape, again nibbling back on spotted owl habitat into 2021, into 2022. You see this sort of erosion back into what seems to be this topographic template of lower hanging locations. When we overlay all those together, what we see are areas in dark green that were persistent through time. They stayed on the map. Areas that were ephemeral, that they came into the map potentially as a function of fire exclusion during that time period, and those in pink were places that were removed from the map as a function of fire. And then here we get to the loose association, but we're trying to increasingly get to a better association. We crosswalk that with our fire refugia maps. So where are the places on these landscapes most likely to persist and resist as northern spotted owl habitat? Do we have some strength and durability in the fire refugia models that we've created to make a prediction about where the best bang for your buck is to maintain those forests? I think we've got a little bit of something here. The Slater fire, that blow-up fire, not so much. Not as much of a relationship, but as we saw from those examples, we're not expecting to see much. There are different behaviors under normal and extreme fire conditions, but there are some fire refugia persisting through there. I'm going to pass things over for the last few minutes to Jeremy to talk about more spotted owl stuff in the context of demographics.
Yeah, sorry folks, you can't make it a full day without hearing something about spotted owls. So I'm going to switch gears a little bit and talk about some of the research that we've recently done looking at the demographic effects of fire to spotted owls. This data incorporates fires from the fire-prone portion of the Northwest Forest Plan area and across 6 of the demographic study areas, the long-term demographic study areas. And if you look at this left panel here, we see we have the apparent survival on the y-axis and the proportion of nesting and roosting cover that is lost due to higher severity fire effects on the x-axis. And hopefully this shouldn't come as too much as a surprise to you, but what we see here is as the extent of higher severity fire increases, apparent survival rates of spotted owls decrease. On the right-hand graph here, we have another relationship between the proportion of nesting and roosting cover that's lost at higher severity fire, but this time on the y-axis we have the probability of territory displacement or abandonment. And again here we see as the extent of higher severity fire increases, the probability of abandonment, territory abandonment also increases. So those should be no-brainers. Some other research we did a few years ago, this is from a subset of the larger data set that I just showed you from fires that occurred in 4 different years using a before-after control impact study design in northwestern California and in Klamath Province. We looked at some similar effects, but instead of probability of displacement, we looked at recruitment rates, so basically turnover of individuals, so new birds replacing old birds on a territory. And on the first graph on the left here, we have apparent survival again on the y-axis, and then we've got 4 columns indicating years in which fires occurred. The histograms on the bottom are sort of the relative proportions of low, moderate, and higher severity fire effects that occurred in those fires in those years. And right away you see the fires that occurred in 1987, 1999 really had no effect on apparent survival rates of spotted owls. I should mention the horizontal dashed line is a group of control birds who were not affected by fire recently. Well, at least since 1987. If we look at the 2004 group, we see, if you look at that histogram on the bottom, we can see that year was characterized by pretty higher severity fire effects, and apparent survival accordingly took a pretty big hit. The 2008 fires were sort of a mixture in between, and we see a little bit of a reduction in apparent survival also, compared to the pre-fire years on those sites. If we look over at the right-hand graph here, here's the recruitment rate estimates, and you see not a lot going on for the first 3 years of fires, 1987, 1999, and 2004. There was no real impact on recruitment rates, but what we see in 2008 is we see a pretty big jump in recruitment rates. So what that's basically telling us is there's more turnover on those territories that burned in 2008. So now I'm going to try to put that into a little bit of context here and tell another tale of 2 different wildfires, but this time using fires that were used in those previous 2 analyses of the slides that I showed you. One being Panther Fire, that again was sort of a normal fire event that Meg mentioned, and the other being a relatively small but pretty intense blow-up fire, the Sims Fire that occurred in 2008. The one commonality between these 2 fires is that they were both had 3 territories that were occupied by spotted owls pre-fire consistently. So if we look at the 2008 Panther Fire, this fire actually reburned these 3 territories that initially burned in the King Titus Fire in 1987. They actually burned another time in between. So these poor individuals burned 3 times since 1987, but I haven't added that to this figure. Both of those fires burned under moderate severity fire conditions, and you can see there's a real nice heterogeneous pattern of burn severity. All 3 of these territories remained occupied after the fire. So if you recall back to that previous graph where we saw the recruitment rates increase with the 2008 fire effects, these birds in this territory, because we think there's these cumulative, from the perspective of a spotted owl, these sort of short interval reburns sort of act as their cumulative effects, right? So these higher severity fire effects, they're not going to go away in a 20-year time span that a spotted owl is residing on those sites. So these cumulative effects have sort of degraded the habitat quality of those areas. So we see a little bit of a drop in survival rates coupled with an increase in recruitment rates. So we think what's going on is the habitat quality in these areas has been reduced to marginal. So these birds can only survive for a couple years before they either die or move on and find a different territory. But the key piece of this is that they're still occupied. So they're still consistently occupied to this day. If we look at sort of the resulting pattern, the other thing I wanted to show you here is, I hope you guys can see it. I was sitting in the back of the room earlier and I was like, oh my gosh, I hope my slides are big enough. But the black squares represent the post-fire owl locations. And you can see they're pretty much generally aligned with those blue lower severity fire effect areas. So then if we switch out the figure with the sort of the persistent nesting and roosting forest, we see again here that those post-fire owl locations are again aligned with where the nesting and roosting covers persisted post-fire. And if you overlay the refugia map on that, we see again there's some pretty good alignment. So what I want you to take away from this is this refugia map does a pretty good job of predicting the persistence of this nesting and roosting forest post-fire. Oh, and also the spotted owls appear to be relating to that somehow as well. So if you contrast that with the Sims Fire, which we would consider a blow-up fire, here on the left image we've got sort of the collection of the 3 clusters of annual locations for those 3 territories. The next right image is sort of the burn severity map, and you can see that large patch of red and yellow basically just erased all of that nesting and roosting cover within the perimeter of the fire. The owls on those territories, on 2 of them immediately abandoned those sites, and they were found, 3 of the 4 birds were found about 10 to 15 miles north of there the next year. The last territory that sort of eked out a little bit of an existence on the sort of southern portion of the burn perimeter, where you see there's a little bit more persisting nesting and roosting cover, stuck around for a couple of years before they left. And I think if we were to sort of go through a time series of subsequent years after this, we would see some secondary fire effects that might explain why those birds eventually left. Interestingly, this is the fire growth model that Meg had mentioned, and even though in this case the spotted owls don't persist in that landscape, we see that even with the fire growth model that the areas where nesting roosting cover does persist seems to be predicted fairly well with that fire growth model. You can see the areas where there's relatively higher probability of refugia. Yeah, the nesting roosting cover persists, but presumably not enough for the spotted owls to eke out an existence. Take homes.
Sure, I'll take us home. There we go. Thanks, Jeremy. Good stuff. So let's wrap things up. Ideas for everyone to take home, what we want to share with you, that there's interpretable predictability in the modeled locations of fire refugia from this fire refugia model suite in both in both the moist and the dry forests of the PNW when we look at this modeling. Accounting for fire behavior in refugia models seems to be critical for capturing those different domains or effects of blow-up versus normal spread events, and I think this is an important part of a lot of fire work moving forward. The fire refugia models validate well with those out-of-sample 2020 and 2021 fires and illustrated refugial capacity of the older forests under normal conditions. We can think of these as locations with longer hang time. I mean, old forests have long hang time. That's how they got to be old. But as we think of these forests persisting into the future, we need to look at the locations that are most likely to persist. What are their topographic templates, their locations, their compositions, and their structure that allow them to persist with increasing challenging fire weather conditions? Spatial pattern and locations of modeled fire refugia seem to be aligning with these northern spotted owl habitat persistence locations and demographic impacts. And so this is exciting for thinking not only about old growth, but for old growth habitat and associated species, and looking for ways to conserve them moving forward. Number 5, lastly, this overall points to a value for conservation planning of old forests and associated species, region-wide and at project level in terms of opportunities. I want to call out, if we've got enough time, a few particular examples for thinking about that application, because this is really where I would love these conversations to go from today. Regional planning, thinking about where the late successional reserve network and old growth forests, again, are most likely to persist through high severity fire events. What can we do with that information in terms of modernization of our Northwest Forest Plan region with that focus on mature and old growth forests? For spotted owl, where are the places that we would be most impactful in removing barred owl, because we're also going to have highest persistence or most likely persistence through wildfire events? Those are regional questions. Project level planning with project teams going through ideas of trying to understand where on landscapes for any individual project area we might use the refugia maps and the high severity maps for thinking about where to make project level decisions related to old growth and early serial management. So I'll thank a whole bunch of people who have contributed to thinking, and we got some question time. Yeah, thanks. Okay.